Everyone, welcome to this week's Crunch seminar. Our first talk today is a joint talk by Professor Miguel Bessa and his student Aleksandr Dekhovich. They would be talking to us about iPINNs, which stands for Incremental Learning for Physics-Informed Neural Networks. Professor Miguel Bessa is an associate professor at Brown University. He obtained his PhD from Northwestern University in 2016 and was a postdoc in Caltech till 2017. He joined TU Delft as an assistant professor in 2017 in the Faculty of Mechanical, Maritime, and Materials Engineering. Prior to joining Brown University in 2022, he held an associate professor position at TU Delft, which he continues to hold. He is also the director of the Delft Artificial Intelligence Lab, Machina. And his student, Aleksandr, is a fourth-year PhD student at Delft University under the supervision of Professor Miguel Bessa. He is interested in catastrophic forgetting problems in deep neural networks. More precisely, he is working on continual learning algorithms for deep neural networks and their application to real-life problems. Prior to joining TU Delft, he graduated from the Faculty of Mechanics and Mathematics at Lomonosov, Moscow State University in 2019. With that, please join me in welcoming both of them for the talk. You may want to take it out.
Thank you very much, Subrata, for the kind introduction. So today we're going to talk to you about continual learning and incremental learning for PINNs. This is not one of those talks where I'm going to show you a bunch of things that we're doing in our lab. We're really just focusing on these topics for this one today. And we split this talk in two parts. The first part is about cooperative data-driven modeling and the role that we see that continual learning will play in it. And in the second part, we will actually talk about the physics-informed neural networks, and you'll see that it segues from the continual learning part that we'll talk about now. And we think that the future of applied machine learning is cooperative because what happens is, as you know, there has been an explosion of the use of machine learning in general in applied science. And everyone is in their own silo, pretty much. Everyone develops their own neural network, typically. You can do convolutional, you can do transformers, you can do recurrent neural networks. You can go to all this beautiful zoo of different architectures and methods in the field. But oftentimes, you do your thing for your problem and you walk away. You can put it on GitHub, but that's pretty much where things end. And as you know, in applied fields like mechanical engineering, material science, and so on, there are many problems that are data scarce. Oftentimes, actually, we run into the trouble of not having enough data about the experiment that we're doing, about the design that we want to create, or something like that. One of the solutions for this is, of course, using physics-informed neural networks, constraining the design space, and having more physics so that you have less data. Another solution is actually to use transfer learning and continual learning. And in particular, transfer learning has been used quite a bit already, but continual learning remains quite unknown, I would say. Even in the scientific machine learning community, there's not that many algorithms about it. And that's what we're going to talk to you about today. So the idea is very simple. Let's say that you are in your lab and you're trying to solve a particular problem. In my lab, often we try to come up with models for materials, constitutive models for materials, for example, but it could be something else. And let's say that you train your neural network, and you perform your task. And then a second lab comes in, and sometimes the task is similar, sometimes it's different, but there's some commonalities to it. And the way to do it nowadays, 99% of the people, what they do is they go there and they train their own neural network, starting oftentimes with random weights or whatever. And that's it. And you need a lot of data to do that. Or you can take what someone else did and you can do transfer learning, keep the weights and so on, and then just start training for your case. But you'll see that actually there's a problem in doing that. And I'm going to cover that in a moment. But the idea is that we want to train for this new task, maybe in a new lab, or we are just doing something else. We want to train this and we want to make sure that we don't forget what the other lab and what the other model was doing, while still transferring knowledge from the past lab to the next one, and so on. This is our definition of being cooperative, because what you want to do is you want to add knowledge, but you don't want to disrupt the knowledge that was accumulated from the past. in the same model. Now, this looks fine, but the problem is that, in fact, currently artificial
Miguel,
neural
can I ask you a question here, because it has to do with the definition of continual learning. Do you have access to all the training data of let's say you are lab 3, and do you have access of all the training data of lab 1 and lab 2?
Excellent question, George. If you hold on one slide, I'm going to get there. In our case, we don't use it, but some people do use it.
Thank you.
Yeah. One moment, and I'll cover that in a moment. It's a very important question, actually. So, but before we get into that particular part, what is catastrophic forgetting and why does it occur in artificial neural networks? So take a neural network, okay, just inputs, outputs, and a bunch of parameters, weights and biases. And then you want to do something with a neural network. You want to train your model to do something. Let's say that, we're training ourselves to learn how to swim. And now when you do this, what you do is your parameters, theta, are updated based on backpropagation. They're updated for particular values that actually will be able to complete the task. So given a particular set of inputs, you are able to fulfill that task. But then you want to do something else. And let's say that you now want to play tennis. Now you go to your network, your brain, if you will, and you retrain your brain to do this particular task, playing tennis. The problem here is that if you use artificial neural networks, you take this network and you retrain it to do something else, as you see, then there's a mismatch. And you actually may have new values for these parameters, these weights and biases, that are overriding the values for the swimming. There's a conflict there. And this is in a very simple picture, basically what happens. You're training the network globally and you find all these values for the parameters and they can clash with what you had before. So most artificial neural networks actually don't do very well. In fact, they do pretty poorly in accumulating knowledge for new tasks, especially if they're quite different from each other. I hope this was clear. I really would like to stop here if there are any questions about this. This is really like the concept part. Was this clear? Okay, great. Okay, so then the idea is, how can we go about tackling this issue and actually accumulating knowledge? Now, the field, like I said, is called continual or lifelong learning. And the entire field is basically split into 3 different parts. You can have continual learning methods that are based on regularization. And that just means that you have your loss function and you're trying to add new terms to the loss that try to prevent forgetting, right? You're rewarding changing parameters that are new, that were not trained before, as compared to the old parameters. But unfortunately, most of these methods, and this is probably the majority, they still do exhibit quite a bit of forgetting, because there's always a bit of leakage, if you will, from the new parameters to the old and vice versa. Then you can do rehearsal methods, and that's what George was referring to. In this case, you are, in lack of a better word, don't get me wrong, but it's almost like you're cheating a little bit, because what you're doing is you're replaying the entire data. It's like you're playing tennis and swimming at the same time, and you're training for the full thing. And in that case, I think it's a little bit intuitive that you're making your task a little bit easier in a way, right? You're replaying the data, like George was saying. Or you can go about this by tackling it with architectural methods, which means that you're trying to do something to the architecture of your neural network to be able to do this continual learning. We are following this 3rd route, which seems to be a little bit less common in the literature. Okay. Now, we decided to go to the architectural route, and we took some loose inspiration from the biological brain. If you think about your brain, what happens is that you actually have different regions in your brain doing different tasks. You have the part related to vision, distinguishing this is a cat, this is a dog. You have a part related to language. And sometimes you can think about this as student, professor, or professor, student. And sometimes the communication can be a little bit tricky. But the point is that you have a different part of your brain associated to these different functions for natural language processing and so on. So we see that the brain actually developed specialized regions for different tasks. And our question was, well, why can't we just do this and try to mimic what the brain really does to some limited extent, of course. And in order to do this, we went about it in a 3-step process. We actually had 3 papers until we got to the point that we wanted to get. The first step for us, the most intuitive, was to follow a pruning strategy. And this, of course, exists in the literature. What you do is very simple. You have your neural network and you train your network. And after that, you prune connections or sometimes neurons, depending on the type of pruning algorithm. But you prune the connections that are less important in our case. And then you retrain the network for the remaining connections. And if the performance is not good, you can still do retraining and prune and retrain until you get a good performance. Now, we have our own way of doing this, and I'm going to walk you through it because, and I'll tell you in a moment why, most pruning algorithms, they're not trying to find space in the neural network for you to learn more things. That's not the idea. They're trying to simplify the model and make inference faster, having lower memory requirements and things like that. But we wanted to minimize the number of parameters, really, even if that doesn't lead to better memory requirements or things like that. So what we thought was, okay, if you have a neural network and you're solving, for example, a classification problem, you have your inputs and you have your weights that you're training for in the biases. What we do is this. We take what we call importance scores. It's a metric that we came up with that is defined by the weights of the connection. So the weight of the connection, the red connection, K, for example, times the actual input value of the sample that you're seeing, okay? Divided by all the weights multiplied by the sampling input for all the connections that come to that particular neuron. So what you have in this importance score is the relative importance of the weights time the input of that neuron as compared to the other connections that you see that get into the neuron. So if you order by importance the connections that go to a particular neuron, you can then prune in such a way that you keep, for example, 95% of the signal. So if you compute the importance, and let's say that the blue connection has the lowest importance, when you take it away, you still conserve 95% of the output by just removing this connection. And this felt like a very natural way for us to keep the network behaving stably, as close as possible to the full network, but removing as the most connections we could for it. And it turned out, I'm going to skip that, but it worked very well. We actually got the best performance compared to a bunch of other pruning algorithms in terms of the number of parameters that we're pruning, and we didn't see any drop in performance. In fact, sometimes we even had a little bit better performance than what you get without any kind of prune connections. But you can take my word for it. If you would want, you could even use a different pruning algorithm that maybe cuts a few less connections. But the point is that we come up with a method that is pretty efficient in cutting these connections. So now, in the continual learning setting, what you do is, let's say that you want to train for a particular task. Let's say the swimming task. So you show a bunch of examples, you prune the network, you train, you prune the network, and if you need, you can even retrain a few iterations, oftentimes very quickly. We get to a small network. And what you get is basically a subnetwork for this full network that we are highlighting in red. Then, when you have a new task, let's say playing tennis, you show new cases. And now, importantly, and that's what is a bit different from other methods, we conserve the full network. So we turn on all the connections that were not trained before, random weights on the black, plus the connections that we trained for which the weights were already trained. And then we prune. And then we prune. And when we prune it, we may or may not prune the connections that were there already. Sometimes you prune all of it and you don't have any overlaps with the first task. Sometimes you actually keep a lot of the connections from the first task. And for the different behavior, the task is not the same as task one, you can use other connections to learn for the difference. In this way, it's a very simple way to say you saved subnetwork one, the original red connection, so you know that it performs that task well. And you now have a subnetwork two that is the blue and the overlapped connections with the one that is able to do task two. And if you save these weights, you didn't disrupt the weights from the red connections, they're the same, and you just updated the weights that are new, you are able to do task 2, and you're still able to do task 1 with the other subnet. It's a very simple idea, but as you'll see, it actually works very, very well. And you can do this for new tasks and so on, and you keep going and having a bunch of new connections, and some of them overlapping with task 1 and task 2 and so on and so forth in a very natural way.
Miguel, can I ask a question?
Of course.
So these are different tasks, of course, but the similarity of tasks would have an effect here, especially the magenta colors. So are you choosing a bunch of tasks from the same hat, but different, how different are these? How do you measure the similarity of tasks, and how do you, you know what I mean? You cannot
I do.
Like you said, from swimming to tennis is 2 different things. So these are very diverse tasks.
Yeah, George, I think this is probably the most important question that we could came up with as well. So as you see, the algorithm is agnostic to the fact that the tasks may be very similar or very different, right? What we are hoping for, and you'll see it in the results, is that if the tasks are really different, then you're naturally going to get to a place where you're not using any of the connections from the other subnetwork, right? But if the tasks are very similar, then you actually see that there's a big overlap between them. And in fact, we did see that. I'm sure we need to test this in many more cases. You'll see that the tasks that we selected are fairly different, but not wildly different. But I'm sure that at some point it breaks down, and it's just better to just have separate networks in the first place if there's really nothing in common with one task and the other. Does this answer your question, George?
Yeah, I just wanted to know if how quantitatively, how, a priori, if you could sort of have some metrics where you measure similarity of tasks in some way, and then you sort of carry on your computations you find, then you come up with some sort of at least rules of thumb for it, because what you're saying is intuitively correct, but quantitatively, I don't know what's going on.
Correct. So we are not doing any a priori computation that biases our algorithm afterwards, but we did simple things. For example, in a regression case, we actually just computed the similarity with a confusion matrix, for example, for classification tasks. We computed how close the curves were. If you have one material and the other, right, you can compute how different those curves are. And if they were very different, you did see less overlaps in the 2 subnetworks that were created for them. But again, I just want to be very clear that even though you can compute those metrics, and we are not using them to change anything in our learning process. Do you see what I mean? So I see that as an advantage, frankly, but yes, in a way, you could also use it to make a better training algorithm too. So you can see it both ways. All right, thanks a lot. This is really kind of a key question. I think we'll touch base upon this a little bit later. Just want to be mindful with the time. Okay, so basically then, just to conclude, we have different subnetworks for different tasks, and they can overlap with each other if that's beneficial for your training procedure. But I did not tell you something that is very important, and for which that neither me nor Aleksandr are very happy with, which is, okay, you can train for different tasks and you have different subnetworks, that's fine. But in the inference, when you're making a prediction, a lot of the people in the field are saying, okay, you already know what the task is. So if you already know that you're swimming or playing tennis, it's not a problem. You just select the right subnetwork and you're good to go. No forgetting, everything is fine and easy. But the harder part in the field is to actually also predict from context what the task is. And here, what we did was we were not very creative. There were some authors that proposed the max output strategy, which is a very simple strategy, but actually works fairly well, which is as simple as this. So you propagate the signal for all the subnetworks, and based on the outputs of the neurons, the correct subnetwork has a neuron that is firing, right? If you're doing classification, the neuron that is associated to that class is firing in the right moment. So it's very clear that that is the maximum output, right? Now, don't get me wrong, we didn't invent this. We also used importance scores as a different metric to select networks, and it worked as well. But this is not perfect because we need a few samples from that task until we actually get to this max output. Sometimes there's a noisy task and it can throw you off and you go into the wrong subnetwork. But if you have a batch of 20 to 30 samples, we tried this in 4 different data sets, we got very accurate predictions of the subnetwork. But frankly, I think there's a lot of work to be done in identifying the right task. In our case, the right subnetworks for the task. Okay, now the results, and then we're back to Aleksandr. So what is the state of the art? The state of the art is, as you probably know in computer science, this big data set called ImageNet with 1,000 different classes. And what several different papers in continual learning are doing, even though they're all fairly recent, they started in 2017 or so, they are basically splitting these 1,000 tasks, classes, into 10 tasks. These are the 10 triangles that you see here. And you learn the first 10 classes, then the next 10, then the next 10, and so on. And what you see is that most algorithms have a lot of forgetting. These are actually the best algorithms that we could get from the different, so this is a regularization method in blue. These are 2 in green are the rehearsals, so you replay all the data. And the red are the ones that are a little bit harder, where you don't replay the data. And you can see that actually when we first published this, we were better by more than 20%. In the meantime, in the same year as DER came up, and we were better about 10, 12% or so than them at the very end of the process. And as far as we can tell, in this setting, we're the only ones that have no forgetting whatsoever. So we keep the performance always up there without forgetting for all the tasks in this big data set, and we don't lose any accuracy. And we were very happy with this, really. Now, I don't want to walk away without telling you the flip side of things. One thing that our algorithm doesn't do very well is that at some point it saturates. At some point we don't have any more free connections, and our subnetworks exhausted the full network that we have. And at that moment, when that starts to happen, you don't have enough free connections to actually learn for the new tasks. And what you see in our algorithm is that at some point it starts dropping off. This is a different data set. It's an easier task, CIFAR 100. But you see that after task 12 or so, we start having some forgetting because we kind of saturated the network. So you would have to grow the network, if you will, to have more free connections in being able to doing this. Before I turn off to Aleksandr, are there any questions on this first part that you would like to?
Miguel, a quick question, Suku here.
Sure.
How do you decide the size of the network?
Yeah, you don't, right? I mean, it's not like we have a metric to tell you that. And this is akin to what happens in standard machine learning, right? How do you decide that you have a big enough, expressive enough network to solve for ImageNet in the first place, right? So what we can tell you, Suku, is that we know from literature already that the networks that are being used are way bigger oftentimes than what you needed. So when you do pruning, oftentimes you get like 5% of the total network being used and the same performance oftentimes. So most of the networks out there are pretty redundant, very bloated, if you will. And that's why
I asked you because of the fact that you showed that, you know, in this case, you didn't have enough connections. So it requires a larger network possibly.
Correct. That's right.
If you go back and use a larger network, do things improve, or how does it work?
They do. There's another thing, I'm glad you asked. There's another thing that we should say. Things definitely improve, but there's also a limit because we have to be able to select the subnetwork, right? So if you have 1,000 tasks, your selection method algorithm, I should say, should also be robust and it should scale properly. And frankly, passing the signal through all the subnetworks is not something that satisfies me, to be honest. It's the state of the art right now, but there's certainly better ways of doing this for sure. And I think that the field still has a lot to grow, to be honest.
Okay, thanks.
Yeah, thank you. All right, if there's no more questions.
Miguel, I have a question.
Sure.
I don't know if anybody has tried connect this to Dropout, because in Dropout you have multiple realizations of geometries of architectures, and therefore, but there's some connections which are common, like you have here, and then you control everything with the Bernoulli distribution and the rate, the dropout rate, and so on. So I know that we use that for UQ, but I wonder is actually if people have looked into it.
Yeah, I know that we're being recorded, but I'll say it anyway. We are looking into it as well. So we're trying to do this also the other way around, George. Instead of going, you train it and prune, to actually do it dynamically. And I should say that an embryonic idea about this is already out there in the literature. And there's also people looking into dropouts, right, to do this. And all of these are viable ways to go about it. I think it's fine. I can't tell you if it would perform better because we haven't done it, but it's an interesting route to pursue for sure.
Right, thank you.
Great, Aleksandr, take it away. I'm going to stop sharing now.
Okay, thank you, Miguel. Let me now share my screen. Okay, can you see it? Can you see my screen?
Yes.
Okay, thank you. So yeah, the second part of the presentation will be about physics-informed neural networks and how we can use these ideas that were introduced in the first part, how these ideas can be used for incremental learning of pins with a single network. And but firstly, let me remind you what pins are. And to do that, let's consider this equation as an example. And what pins do, they parameterize the solution as an output of the network, as you had. They take the X and T as inputs, and then after computing the output of the network, they take the advantage of automatic differentiation to compute these residuals, R subscript F, R subscript P. We compute these residuals, and these residuals form the loss for pins. And the training process is basically optimizing the weights of the network by minimizing the loss L. And here we have the expressions for every loss term. And basically, every loss term consists of these residuals. But for pins, the task means a bit different thing compared to image classification, for example, in continual learning. There is a difference or several differences. First of all, what do we mean when we say task? Task, it's PD itself and its initial and boundary conditions. And there are two differences. First of all, in the formulation that I presented in the previous slide, we have access to our inputs, our X and T at every moment of time, meaning that it's not exactly continual learning for pins, because as Miguel said, in continual learning, we either don't have access to all data, or we have access to small fraction of all data. But here we have our inputs, X and T, and we can easily sample them. So there is no such problem as data scarcity. And this is some bonus that we have in this case. But there is one problem. If we have one network, we cannot learn two PDs with this one network without modifying its architecture. So what I mean, if we have this simple network with two inputs and one output, and we have our inputs X and T, and we learn firstly one equation, and we obtain our solution U1 hat, which is the output of the network is parameter theta and given X and T. And then we have another equation, and we learn its solution, and we parameterize this solution exactly with the same network, with the same theta and the same X and T. And there is no way that these two outputs will be the same. So the same network cannot simultaneously with the same single output neuron learn two solutions. So we need to do something about this. And there are two main questions: how we can learn incrementally pin, and what's the point of this? What we can gain from this? In other words, can we reduce the prediction error by doing this? And the main idea is basically the same as for continual learning, with some small change. So yeah, we split our network into multiple subnetworks, and with every subnetwork we associate its PDE or task. So in our case, PDE is the same as task. The training stage for task 1 is totally the same like in image classification. So we have our network, we train it, we prune and retrain this network as many times as we need. In the end, we obtain this subnetwork. We save this subnetwork, and we associate these red weights to this to the first task. This is totally the same like an image classification. Then we have the second task. And again, we have some weights that are associated to the first task. So we have some free connections. We prune network, retrain, and we have our second subnetwork. And again, we have some overlaps. But here is the difference. In continual learning version, we fixed the weights that were associated to the first task, and these weights couldn't be changed. Here, since we have data, I mean our inputs X and T, we can easily update these overlap parts to make this whole construction more flexible. And here is basically how we do this. So in case of two tasks, our loss now consists of two terms. One term is associated to the first task, the other to the second. So there are two sources in this loss. And when we perform backpropagation and compute gradients, we just need to do it with respect to the subnetwork to which and every connection belongs to. So, for instance, for this current connection, it belongs to only the first task. Therefore, our gradient will be computed only from the first term, the loss. This connection, it's associated to the second task, and therefore the gradient will be computed only with respect to the second second loss. But for this magenta connection, there are two terms in how we compute the gradient, because this is the connection that belongs to the overlap. And this is the main difference from a continual learning version of the paper for image classification. Here, yes, here we have data, I mean X and T, and therefore we can adopt overlaps. I see there will be questions.
Aleksandr, I had a quick question. If you reorder the task 1 and task 2, do you get the same result?
This is a good question, and we have one set of experiments about this case. In general, for our results, yes, the procedure is robust to task orders.
By yes, meaning, yeah, we did it and it works for different orders. So, yeah. We did it actually quite extensively and with many data sets, just to be sure as well.
Yeah, for image classification, we also did this for multiple orderings. So, right. For instance, for CIFAR, the results were averaged over 5 different orderings. So,
but your network connections for the magenta might be different.
Yes, or? They can be different. What is close to what numbers are close are the numbers of total percentages of magenta connections or some other overlap parts, and I have slides about this. Yeah.
Okay.
Let's see this. Okay. Okay. Then we have the third task, and we repeat this procedure. Some weights are associated to the first task, some to the second, some to the both. But still, we can prune this network, and we can assign the connections that are remained after pruning to the third task. And here we see many colors, meaning that now we have more overlaps. Some of the connections belong to all of the tasks, some to any two of them. And in the end, we see some picture like this, where we have connections that are associated to only one task. We may still have free connections, and also many connections that are associated to multiple tasks. But these overlap parts can be, again, easily overlap in this case, because we have access to X and T inputs. Okay, these are our experiments. So we have 3 set of experiments. two belongs to one learning scenario, and the last one belongs to a bit different learning scenario. But overall, our experiments are set like this. So we have a set of PDEs. We can see the one-dimensional case. So x belongs to from 0 to 2 pi, t from 0 to 1, and we have periodic boundary conditions for every equation in this set, and we have the same initial conditions for every equation in this set. So the difference comes only in the set of the equations. What is important is how we measure loss. So we measure loss with two ways. Relative error and absolute error, but the tricky part is here. So you see, for instance, here for relative loss, we have two subscripts, L and K, and that means that this is the loss, the error, sorry, on task L after we learn task K, because future tasks may influence the performance on past tasks. Even though we retrain our subnetwork, still the error never the same. So we track the history of errors while we learn new tasks, and we track not only the history but also forgetting metric. And by forgetting, we mean it's called backward transfer metric. We compare the error on task L after we learned task K, and error on task L after we just learned task L. So what it becomes minus what it was in the very beginning. And we average this across all tasks that I learned so far. Yeah, this is how we measure the error. So standard error, relative and absolute errors, but also we should measure forgetting part. And the first example is this 1D convection problem. And here we have this parameter beta. That
Aleksandr, can you go back to the metrics? So this will show incrementally how you learn, but how do you actually know that you have where? Oh, I guess from the BWT, because the error compared to, let's say we have the exact solution, the exact solution doesn't come in at all, right? It's only how you improve the error.
That's correct. That's correct, George. Yes.
In other words, you may be going down the wrong lane and you have no clue. If because you will be learning the new task better, but compared to the previous task, somewhere you have an anchor point, so to speak, where you know that you learned the first task correctly. Within a, you know what I mean? I don't have a feeling that how accurate my solution is. If your first task is 100% error, how would you know that? Unless you also have an error for that independently.
I'm not sure that I understood the question. Well, first of all, yeah.
Look at the definition from your left. So let's say we know the exact solution.
Mm-hmm. This is U. Mm-hmm.
No, this is UL is the one that you learn.
No, sorry. So I learned U hat is output of the network.
So UL is the reference solution.
UL is the analytical solution.
Oh, I thought it was like a successive.
Sorry.
I thought UL is like ULL or something, but okay, I got it. Okay, yeah, no problem then.
Okay.
And then you go as you evolve, right? You have now new tasks, and that's why you have the L and the K. You have to see what happens as you learn more tasks, right?
Yeah, it makes sense. No problem. It's my bad.
No
Sorry,
problem.
yeah, I should have told that. What is the prediction and what is the analytical solution? The first problem is 1D convection problem, and here we have this beta which we can change and out of which we form our tasks. Here we see the analytical solution, and you see that with the increase of beta, beta influences the speed of change for the solution. And these are our results. So we compare iPIN, which is incremental pins, and this is the error after we learned all the tasks. So this is the error for every task in the end of the training procedure. Okay, and compare this with regular pin, and we see that after iPIN learns the first task, it uses the weights from the first task, part of the weights, of course, I mean, subnetwork only, as a good initialization for future tasks. And that helps a lot. So this is called forward transfer, when past tasks help to learn future tasks. We also have some forgetting, but it's really a small value compared to the errors.
Aleksandr, for this equation, we had somebody from Berkeley like a year ago who showing that basically you need to use continuation methods to solve this. So then you don't get to this 37% error. If you,
of course,
yeah. So of course iPIN does it automatically, but they will do it manually where you have continuation on beta, right? So it's kind of similar idea, but more manually for them, yeah.
Yeah, I think. Yeah, I think you are referring to the work there. There was used curriculum learning. Regularization. Yeah, that's where we basically took these benchmarks.
Yeah, exactly.
Yeah, and also we can see the history for the error. So on the diagonal is the error after we just learned the task, and the last column corresponds to the final result here. So the last column is exactly the same as this column. So by rows, we can see the errors for the task, the history of the error. And we see that if we look at the diagonal and compare this with the final column, we see that indeed for every task we forget a bit. And we see this also in backward transfer. But this forgetting is not very significant, I hope, and that justifies the idea, and that we don't forget much.
Did you use Sukuya? Did you use a sign activation or?
Yes. We use sign activation for every experiment, not only for this convection with initial condition as sign, but also in other one where we have bell-shaped form. Initial condition, still we use sign. We use sign in every experiment. We actually did a comparison for sign and hyperbolic tangent, and sign worked better everywhere.
Sorry, I have another question, and this is not to undermine your work, but if I take the a neural operator like the DeepNet, for example, and I put into the trunk beta here for this problem, I can solve for not just discrete values of beta. I can solve for continuous values of beta for a whole distribution. So I can learn with one network. I can learn to solve this equation without any with just a vanilla neural operator, right? You see what I mean?
Yeah, you're correct.
And if you want, of course, you say, well, you don't have the equation. You can do physics-informed DeepNet. So the training will not be in the law. So so in that case, the same weights will give you, because you're learning a higher dimensional operator in some sense.
That's right, George. I would just add one thing, Aleksandr, that the idea here is to show that, of course, you can have more parameters. And we talked about that as well, Aleksandr, right? Just put beta as an input as well and things like that. But your space is also bigger. And sometimes traversing the loss, as we know, can be tricky, especially in the context of having physics constraints and so on. So here's just a demonstration that if you have these sort of discrete equations, and you'll see in the next example that they could actually be different physics as well, diffusion, reaction, advection, whatever it is, that you can constrain the space. And now you're just learning for time, for example, right? And it works. But you certainly can broaden it up, put all of it as parameters, and learn it with one single network, with one single task.
So Miguel, the basic idea is, even if you have a high beta, that you start with smaller values of beta and keep learning as you go along, or?
I think the idea is we're hoping that it's actually broader than that. The beta is just an example that we found in that paper that you just referred, that it was showing that it didn't work. But we want to push this into even different PDEs if you need to, right? Different parameters, whatever it is. It's not the beta is just the simplest demonstration, the first example, if you will, to explain that you can put even the same PDE with a different parameter and learn for it as you grow the number of beta. Does that answer your question, Suku?
Yeah, because I sort of, I don't know, I was thinking about, when we do nonlinear computations, for example, like when you have a load step for something, right, you want to go very far. So you actually, you go in increments because you want to trace the load path, right?
That's right.
So,
yeah, that's true. Yeah, you could definitely do something like that. And we're even now testing, again, this is recorded, but anyway, we're testing to see what happens if you actually have different time domains as well and learn betas in different domains as input, that we haven't tested. Don't get
just another another remark was that, it sort of reminded me of this notion we were talking before also. It's like in some sense, the approximation angle compared to what we were doing before is sort of like a domain decomposition kind of idea, right?
Yeah.
Where
yes,
you
exactly. Yeah, you can do something like that too. I think we can do something like that too. Yeah.
Right. Anyway.
Yeah.
For the second example, we have reaction equations, and here we can change this rows and from 1 to 5, and this as the solutions. And here, as I think, the solutions, looking from the images, we can say that solutions are more similar to each other, meaning that they don't change very fast with respect to the change of row, which makes the tasks more similar. And that's what we see also from our results, because we obtain a very low error for iPIN for every case, but also we have negative backward transfer, meaning that future tasks help to improve past tasks. And this is possible, I think, because tasks are more similar. And if we look at the history of the loss, we see that for every equation, the value in the last column, so the very final result after we learned all tasks, the error here is lower than the error on the diagonal. So we could improve every task. So for every task, as process goes until the end, the error reduces while we learn new tasks. And this also represents that's also represented by negative backward transfer. This is the second example of this first learning scenario. But we also have another example and another learning scenario. Here we have reaction diffusion, and here we have two parameters. And this is the solution for reaction diffusion under parameters rho equal to 4 and nu equal to 4. If nu is equal to 0, this is a reaction equation. This is a solution for rho equal to 4. And if rho equal to 0, this is a diffusion equation. So the reaction diffusion consists of two components, reaction and diffusion. So let's learn firstly reaction equation, then diffusion equation, and see how well we can learn reaction diffusion. We can also change the order, meaning we can firstly learn diffusion, then reaction, and then reaction diffusion. So the idea here is to learn firstly components of the composite process, and then learn the process, the final process itself. And here are our results. So again, these are errors after all tasks are learned. On the left-hand side, you can see when reaction is learned first, then diffusion, then reaction diffusion. On the right-hand side, when diffusion is learned first, then reaction diffusion. The good thing that we can improve reaction in both cases, which is nice. Again, we have some sort of backward transfer apparently from reaction diffusion. The bad side of this example is that actually we couldn't improve diffusion and reaction diffusion. The values are very similar. These are averaged over multiple runs. So diffusion in reaction diffusion couldn't be improved, but we could improve reaction, of course, compared to regular PIN.
But the error was already pretty low, to be fair, right?
Yes, I think one of the problem is that PINs can learn, for instance, diffusion equation itself really great, so there is no much room for the improvement for diffusion, for example. But we analyze one more thing with this example. This is subnetwork analysis. So let's look how many parameters and how many parameters I assign to every subnetwork. And for both cases, when reaction is learned first and when diffusion is learned first. So these are the circles. So the gray circle represents the full network, or 100% of the parameters. And for example, so for instance, this red circle corresponds to the reaction. And for instance, this 11.8% means that 11.8% of the parameters are assigned to reaction only to the reaction. And for example, this 31.8% of the parameters are assigned to all three subnetworks. This is when we learn reaction first. When we learn diffusion first, to some extent, we see similar picture. So, for instance, 31.5% of the parameters assigned to all three tasks. The same, it's almost the same number as 31.8% here on the left side. Also, for instance, diffusion. For diffusion, we see 11.3% of the parameters that are assigned to only diffusion. And diffusion was learned the first. In this case here on the left, reaction was learned the first. And 11.8% of the parameters were assigned to reaction. So when we can see the only parameters that were assigned to the first task, the numbers are very close, 11.8 and 11.3. And also, if we sum up all these numbers on the left and on the right, we obtain about 80%. As far as I remember, 79.5 in one of the cases and 79.8% in another case. So no matter how we construct our subnetworks, no matter what is the order of the tasks, we still obtained the subnetworks, and total number of occupied parameters is almost the same for both of these orders, which gives us a hint that this procedure is robust not only in terms of the error, but also in terms of the how the subnetworks are constructed overall. So how many parameters will be assigned in the end, which is really great to know if this is true. I mean, this is a really great property for this approach.
Just let me add one thing so that we don't keep only positive. Of course, you also notice that it's about 80% of the parameters that we used already, and these were just three tasks. Again, the size of the network does matter. At some point, we will saturate all the possibilities that we have over there, even though here, we're actually updating connections that are shared, which is nice. It lowers the number of parameters that can be used. The other thing that is, we found it curious was, you see that if diffusion is learned first, you have these 11.3%. No, it's fine.
Sorry.
You have this 11.3% of parameters being used, but if reaction was learned first, you have these 11.8% parameters being learned first. Do you see on the left and the right? And reaction is the one, I believe, that is harder to learn compared to diffusion, but still we're using the same number of parameters. I found that interesting. And again, none of these numbers are preset. These are naturally born numbers, if you will. They arise from the procedure. I hope this was clear. Go ahead.
Miguel, I don't know if it's a thought or a suggestion also. Have you, it'll be interesting to look at, if you look at, say, compressible elasticity, and then you go into incompressible elasticity, right? That's
so, Mark, can you say that again? I couldn't hear you. I'm sorry.
Oh, no, I meant, an interesting problem might be to go from compressible elasticity, right?
Yeah.
To nearly incompressible elasticity.
Oh, yeah. Okay.
Right? Because that's where all the problems arise, right?
Yes, I see. That's an interesting
thing. Because it's, it gets tougher and tougher, right? As you increase Poisson ratio.
Yeah.
Right. So then it will really show, because there, it might, there I would say transfer, this sort of learning might help a lot, right?
Yeah, no, this is great. We did try it for material models as well, not iPINNs, but the continual learning strategy, CPNS, to learn constitutive models for different materials. We didn't try compressible and incompressible in that way, but we tried different plasticity models, for example, and we see similar kind of behavior. You see that you need less data, that you're transferring knowledge from one to the other, and sometimes The models actually look quite different, but there's still some level of transfer. You almost seem to gain something all the time, you know, which
Yeah,
is
sure.
it's a really cool thing.
Okay. Well, basically, to sum up, first part was about continual prune and select, which is a continual learning algorithm that creates overlapping subnetwork. And this subnetwork, they do not forget information. The parameters, they're fixed as they are created. And we showed the best performance up to date on ImageNet 1000. But there are two issues. The first is network saturation, that at some point you don't have enough free connections to learn new tasks. And subnetwork selection that Miguel also mentioned, that the more tasks we learn, it becomes more difficult. By even if we have a small number of tasks, we need a batch of data, test data, to predict correct task ID and as a result subnetwork. However, for example, for ImageNet 1000, we showed that it's enough to have 5 test images to predict subnetwork quite accurate, but still it can be improved. Relating to the second part, we presented this incremental approach for PINs with single network without extending its architecture. We showed the forward transfer for when equations belong to the same family, for instance, only the family of convection equations, or only the family of reaction equations. We showed with these circles that the procedure is robust to task order. So when we change the order of reaction, then diffusion, or diffusion reaction, it's robust in terms of the error, and also in terms of the how subnetworks are constructed, how many parameters are occupied overall. However, we cannot guarantee knowledge transfer for every case. Again, for example, for this reaction diffusion case, we saw that for diffusion and for reaction diffusion, we couldn't improve the error, maybe because the tasks were simple, maybe because they were not very similar, but we couldn't improve the results for these two equations, only for the reaction. So there is no guarantees. That's it. Thank you. And we are happy to answer the questions.
Thank you, Aleksandr. That was amazing.
Great results. I really interesting also the percentages that you have. I think Subrata has a question.
Did you try transferring across different domain shapes?
No, so every experiments that we performed were under the same domains. Yeah.
So Subrata has published a paper in Nature Machine Intelligence for transferring domains, but also she has a published paper where she's doing multitasking, where the equations change. For example, what you did is you parameterize the equation, but you could have, imagine the Fisher equation, what's called the Fisher equation. You just had one term, U1 minus U, for the reaction, but there's actually a whole bunch of different forms of the equations, including an exponential source term, which is for combustion cases, for example, versus other cases. So those will be a little more tricky to go from a source that is exponential to algebraic. And I think Subrata has some experience, but I think she's hiding her results.
Yeah, we didn't finish writing the paper. We still have some things to do, and we are on a writing process right now.
But this is not Miguel and Alex. This is not. This is an operator learning. That's why it would be interesting to consider to actually. It could also be used, like we could use your pruning technique in our operator, so to perhaps reduce the number of parameters, or maybe increase the accuracy. Because what you found is kind of interesting. If you look at the paper by I think DeepMind or Google, the Gatto paper with 600 tasks, they couldn't really figure out if there is a synergistic effect or not, like Alex was talking about. But you sort of quantify that, at least for this parameterized PD, which is the same, you have a synergistic effect, that's what the cooperative concept that you introduced, Miguel, is about synergism. Is there synergism
That's
and
right.
therefore you actually learn from one test to the other. So that's really, really interesting stuff.
Aleksandr, correct me if I'm wrong, but we've done the pruning technique, George, for convolutional networks, recurrent neural networks, standard feed-forward neural networks. So at face value, I don't see any real block in applying this to a deponent. Yeah. I don't know if you have anything else to comment, Aleksandr.
No, in theory, it's applicable to
Yeah,
every architecture.
I don't see any.
There is no
issue.
any limitations.
Yeah, I think so too.
So the basically strategy is about, let's look how signal propagates and cut the connections through which a signal is not very strong.
Exactly.
And that's it.
And we even
Maybe
Miguel,
that offline you can talk with Aleksandr and see if
Yeah.
there's any benefit by doing that on deponent and actually exchange some ideas of your unpublished work.
Yeah.
Okay. Yeah, that would be great.
Yeah.
Do we
Any
have
more questions?
If not, thank you, Aleksandr, and thank you, Professor Bessa, for tuning in today.
Thank you.
Thank you. So I just want to say one thing. I apologize. I cannot stay for the next speakers because I have to be with the undergrads now, but I wish you a great rest of the seminar. Okay. Thank you very much.
Bye. Yeah. Bye. So we move to our second talk. Our second talk is by Subrata Mukherjee. You may want to share your screen. Hi. I could introduce you in the meantime. Yeah. So he would be talking to us about machine learning-based improved NDE methods for defective diagnostics. He is currently a fifth-year graduate student in the Department of Electrical and Computer Engineering at Michigan State University. He is advised by Professor Yiming Deng and Professor Lalita Udpa at Non-Destructive Evaluation Laboratory in MSU. His research interest lies in non-destructive evaluation methods and signal processing techniques, and his dissertation work focuses on the development of modern machine learning methods based on improved automated NDE for defect diagnostics. During his PhD, he has designed novel new sensors and have collected vast amount of smart sensing-based NDE data in wide range of applications. Based on the new age datasets, he has developed novel data analysis algorithms that can identify defect characteristics with very high precision. Before joining his PhD program, he has worked in the telecommunication sector at Ericsson for 3 years and has a summer internship at Analog Garage. With that, please join me in welcoming him. You may want to take it away.
Yeah, thank you, Subrata, for the brief introduction, and also thankful to everyone for giving me the opportunity to present over here. So today, good afternoon. First of all, today is my screen visible, right?
Yes.
Okay, sure. So today I will talk a brief a portion of my thesis, which talks about the machine learning based improved NDE methods for the defect diagnostics. And I am a final year PhD student in the non-destructive evaluation laboratory at Michigan State University. So first of all, in the overview, I'll talk a little bit about the introductions about what NDE is and what are the applications. Then I will briefly talk, mostly talk about the two main projects. One is the spatial reality image denoising, and another is the hybrid deep learning framework for autonomous inspection of the plastic pipelines. Then I will just give a brief overview of the other talks, what is the multimodality executions and dynamic defect tracking by the virtue of transfer learning. And then I will conclude. So first of all is the introduction. What is NDE? NDE stands for the non-destructive evaluation techniques, which is made up, which comprises of several physics-based sensing techniques that depends upon the inspections of the materials, what we are inspecting. And depending upon the material, we develop various sensors because the material, because of the, as it ages, there are wear and tear of the materials. And to make health inspections of those structures, NDE comes into play. NDE comprises of a set of non-invasive inspection techniques. And as these are non-invasive inspection techniques, hence When the materials are in inspections or in situ, that means when they are in service, then NDE comes into play. Because of that reason, NDE finds this advantage or applications in a wide range of industries. So it can be applied in pipeline industries, nuclear power plant, aerospace, railway, and currently it has been rapidly used for the electrical vehicles, state-of-the-health estimation of the EV batteries. Now, what is the need of the hour? Due to the development in the additive manufacturing and in other domains with the composites, there is a development of the smart materials which need smart inspection services, which our NDE community has coined as NDE 4.0 and NDE 5.0. Now, there are two broad sectors of the NDE 4.0. One is the development of various low power consumption wireless sensors, and another, which is the area of interest over here, is to develop the automated big data analytics algorithms that can perform robust, efficient defect detections and diagnostics without much of human intervention. As I have told that there are two broad stages. One is the data acquisition. So from the transducers, we are generating a signal that is getting interacted with the material and the test. And from that, from the receiver, we are acquiring the signals. After that, we are doing the defect reconstructions by various ADOF signal image processing algorithms. And after that, we are doing the defect diagnostics. But in order to perform the defect diagnostics, which can be either detections, localization, classifications, assessment, or the prediction. Prediction is the remaining useful life in order to find out. So we have to understand, first of all, what the problem is. Then we have to find out what is the physical significance of the data that we are getting. And after cleaning and structuring and doing the data evaluation, we have to model the algorithms so as to make them interpretable and then perform the accurate defect diagnostics. So as you can see, once we do the raster scan of the by defined sensing methods, so we get in the form of images by doing the raster scan. And in my thesis, actually, I have developed various sort of cheap, naive, easy to make sensors based upon the laser profilometry based setup. As you can see, it can form circular rings inside the plastic pipelines. Whenever a defect will come, that will cause a distortion in the laser rings. Another is that I have developed some capacitive imaging based sensors also that gives the result in the form of the voltage outputs, as you can see. And there can be another sort of sensors called the magnetic flux based sensors or eddy current based sensors. These are heterogeneous sensors where the output is magnetic flux, and another is the output can be either complex impedance or voltage, and another can be hybrid technique comprised of microwave induced thermoacoustic imaging. So in my first talks, I will talk about especially adaptive NDE methods. This work of ours has been published in the Journal of Applied Physics, and here the goal is to, first of all, to gather the data by developing a high Q factor based capacitive probe. Now, in the real experiment, the data can become very much noisy due to the liftoff. Liftoff means the distance between the sensor and the material under test, and also because of the other drifts like the probe tilt in the probe, or because of the uneven sample surface, or because of the other uncertainties or variations in the data acquisition rates. Now, what's the goal? The goal here is to detect the defect under these noisy regimes. For that, in order to understand the noise, we have developed two models. One is the Bayesian decision theory based approach based upon the compound decision theory that takes into account both the weighted and unweighted classification laws that I will discuss. But the bottleneck of this theory based approach is that it takes into account some oracle framework or oracle information, hence which is not always available in real life, that oracle information. For that, there is a need to develop a non-parametric, solely data-driven model that we have developed in the later stages. As you can see, this is the in-house sensor that I have developed. This is an LC tank-based probe which consists of a capacitive probe, basically, which consists of a parallel plate capacitor, which has strong fringing field along the edges, and a coupled inductor. Now the working principle is as follows. So whenever a conducting material comes, and whenever there is some defect or some distortions, there will be change in the dielectric constant of the material because of that defect. Now that will change the capacitance, and thereby that will change the resonance frequency, because there will be a shift in the resonance frequency, and that is captured by our probe. And this is basically the experimental setup. After characterization, we have used a 5 megahertz RF source that is going to the power splitter, and which is thereby going to the directional coupler. And the directional coupler is generating from the probe. We are getting the reflected signal, which is going to the lock-in amplifier. The lock-in amplifier is generating a voltage output that is proportional to the difference between a reference signal and the reflected signal that we are getting from the probe, which is going to the NI-DAC unit for the processing and digitalization. And after that, we are getting the image in the computer by some MATLAB and Python codes. Now, I have done the experiment on 12 various experimental scenarios, and each experimental scenarios are at 3 various liftoffs. As you can see, these are from the raw voltage readings across 3 experimental scenarios, and each experimental scenario has 3 columns on the basis of a no liftoff, 3 mm liftoff, and 5 mm liftoff. As you can see from here, that with the increase in the liftoff, the difference in the voltage readings between the defective areas and the background decreases. These are the defective areas, but when the liftoff increases, with the increase in the uncertainty, the difference between the voltage readings between the defective and the non-defective areas decreases. And also you can see, because of the drift in the probe and also because of the uneven sample surface, in the background actually there is some distortion in the signal that is also causing the uncertainty. Now then we try to figure out whether the noise that has been incorporated because of these uncertainties, whether they are spatially dependent or not. Then by this hypothetical F test, we find out that the null hypothesis fails. That means that the noise is spatially dependent on the locations. Later, we wanted to find out the heterogeneity in the production. For that, how the noise is spatially dependent on the location. For that, I have treated it as an bivariate normal mixture model, where these yi's are the voltage readings at different locations for different experiments and for different liftoffs. Whereas, so I'm telling that if for a point is coming for a defect cluster, then it will come from these distributions with these deltas and sigmas of the parameters of this distribution. Otherwise, it is coming from this distribution. But in real life, we don't observe this theta in this estimator. We only observe this voltage readings. Hence, what we are doing, we are taking into account for this theoretical framework some contour plot-based thresholding, because at lower liftoff from these raw voltage values, the defect size can be approximated by some contour plot-based thresholding or by some segmentation. But at higher liftoffs for the same experiment, actually for the same experimental case, for the higher liftoffs, we can't do that. So what we are doing, we are superimposing the information that we are getting from the lower liftoff to the higher liftoff cases, and then we are doing the estimation. That's why I am calling it as an oracle framework. Once we do that for each of the experimental scenarios across 3 liftoffs, we know the parameters of each of these distributions, and from that I have plotted the 95% confidence interval, where the confidence intervals of the non-defective points are in the light gray, whereas that of the defective points are in dark gray. And these red points are the mean of each distribution. Here also you can see that it's clearly evident that the difference in the voltage readings between the defective and the non-defective areas decreases with the increase in the liftoff uncertainty. That you can also see from this violin plot distribution too. Now, once we get the parameters of this distribution from this marginal distributions, so we are reporting the base misclassification error and also the false negatives and the false positives based upon this oracle information. Now, what is false negative? False negative means our estimator is telling a point to be non-defect, but in reality, it's a defect. The false negatives are very much detrimental in NDE, and that has to be controlled as much as we can. Whereas false positive means our estimator is telling a point to be defect, but in reality, it's a non-defect. Though false positives are not so detrimental like that of the false negatives, but having a higher volume of false positives will incur unnecessary cost. So the goal is to minimize both the false negatives and the false positives. Also, another thing is to be noted that in biomedical imaging also or in NDE, the proportions of the defective areas or the maligned areas are very much small compared to that of the non-defective or background areas. Hence, we have to control the false negatives that I am controlling here by a weighted classification loss model. I am keeping the false negative control below 10% at a 10%, and by doing that, I am minimizing the false positives by varying these weights within 0 and 1. We vary the weight and treated it as a weighted classification problem. We do it as we wanted to get an entire curve of the false positives and the false negatives. And this is the decision rule that is governing this minimization of this cost function. So let me clear this by this plot. As you can see, this is plot for one such higher uncertainty cases for one such experiment, where the green one is for the higher liftoff, the blue one is for the medium liftoff, and this golden one is for the lower liftoff, where we are plotting the false positive versus the false negatives by varying the weights, where weight equal to 1 means the unweighted classification loss model, whereas by varying the weights, we are getting these curves. Now, when we are constraining the false negatives to be around 10%, and we are choosing that false positives, the minimum false positives from here that are demarcated by these red marks, as you can see. Another thing that is to be noted, that when we are constraining our false negatives with the increase in the lift-off uncertainties, the false positives are also increasing. Here, across all the 12 experimental regimes, for each of these 3 lift-off cases, we are reporting both the false positives and the false negatives, and also the base misclassification error by both the weighted classification loss and by the unweighted classification loss. And we have shown that we are getting lesser than 10% actually exceeding in our theoretical loss model. However, in our image data, actually we have getting the readings in the form of the grids. Then we can treat it as a point-by-point classification problem, where the null hypothesis or the null distributions will come from this normal distribution from the background, whereas the alternate distributions will come from the defective areas, say. But doing a point-by-point classification is next to impossible, as we don't know the location and the size of the defect. Note, in our Oracle framework, in the previous case, we are doing some sort of Oracle framework that is not always present in the real life. So what's the remedy? The remedy is to combine the information from the neighboring grid points. Here, we are combining the informations by an ensemble of filtering technique in various steps. In the first steps, we are applying a spatially adaptive filter based upon the local variance in the signal. Here, for every scan point, we find the mean and the variance of the readings from its neighbors using some kernel weight. We consider the neighbors and we weigh the neighboring readings based on their distances from the scan point. Then, if the variance is greater than some certain C1% quantile of the threshold, then each scan point is treated as a defective point as shown in the red, whereas others will treat it as a non-defective point. But there you can see that though we are minimizing the false negative, but here we are getting a higher volume of the false positives. Why this is happening? This is happening because of the drift in the probe and also because of the uneven sample surface. As the voltage readings are very high over that region, hence that causes a high variance. Next, we are applying a naive filter where just we are applying a thresholding out the high raw values. Based upon the raw values, then we are applying a naive filter, and we are telling that if it is below a certain C2 threshold, we'll tell it as a defective point. Otherwise, we'll treat it as a non-defective point. Then in the third stage, we are doing multiplications of the previous two filters, and then we are applying an average filter to smooth out the sporadic non-defective misclassified scan points. After that, you can see the false positives has been greatly reduced. Finally, we are doing a binary classification conducted by a thresholding parameter, and after doing that, we can localize the defect, and there the false positives and the false negatives has been significantly reduced. You can see from here. In the next case, actually, we have compared our algorithm that is across all the 36 experimental regimes. So where our method is given in green, and we have compared it with the other competing models that are in market in terms of the thresholding based upon the raw voltage, that is in black, and also based upon the low rank model based denoising, that is given in red. Here coverage means 1 minus false negative. So higher coverage and less false positive is expected. So you can see across all the 36 experimental regimes, our algorithm is giving better coverage and lesser false positive in almost majority of the cases in terms of the other competing algorithms. So this was one of the work, and I'm just briefly covering the other spatially adaptive work that have been done in my initial years of the PhD. So here, this was also another spatially adaptive work. There, I'm just going over it due to the shortage of time. That work has been published in the Journal of Non-Destructive Evolution, Diagnostics and Prognostics. So there, the goal was basically because as you know, if we are doing an extensive scan of the pipeline structures or whatever structures we are scanning, that is very much time consuming and costly. So what's the goal? The goal was can we compress the amount of the stored data? So that means instead of taking all the rows of the scans, can we compress and can we develop some algorithm that by the virtue of which we can tell that we can predict or estimate the defect size properly. So there we have I have developed a cleaning-based spatial interpolation-based algorithm based upon the magnetic flux linkage data. The magnetic flux linkage sensor I will discuss later. So that I have developed by both the simulations. The simulations are being done in the 3D console multiphysics, whereas the sensor has been I have developed the sensor by using some magnets and also a Hall effect sensor for getting the magnetic flux linkage signals. So as you can see, once I gather the signal, I have done an undersampling at uniformly random tuning scan points. Then I have used a cleaning-based spatial interpolation algorithm to reconstruct the NFL at all the points. Then I have used a thresholding-based segmentations to detect the defective areas. After that, I have evaluated that by terms of performance metric like adjusted R-square, coverage, and also exceedance, where high coverage and low exceedance are expected. So I'm just showing a single result based upon our application of the cleaning on the experimental data as well as on the simulation data, where it has multiple defects. As you can see, this one is the 3D plot and the 2D plots. Based upon that, actually, when we are increasing the subsampling rates, that means we are taking into account lesser informations of the sample points in our grid from our grid, and we are predicting on much unknown points. by doing that also, we have achieved more than 90% coverage and less than 1% false positive rate, even on using only 4% of our MFL data, true MFL data that we have achieved in our paper. So that was just a brief of the framework that I discussed. In the next project, actually, I will talk about a deep learning models for the defect localization and also the classifications in the plastic pipelines. This paper of ours has been published in the Journal of Non-Destructive Evolution, which is a Springer journal. Here, there is a need to develop an integrated diagnostic framework for inline inspections and to perform an automated defect characterization. I have developed a nice cheap laser profilometry based sensor that consists of a laser source and a camera, which are stationed on the same optical axis, but in the opposite direction, as you can see from this image. Now, why we have to develop a laser profilometry based setup? Because the traditional NDE techniques like magnetic flux leakage or the eddy current that works mostly on the conducting specimens like the steel samples or the aluminum samples, but that doesn't work on the high density polyethylene plastic pipes. For that we have to develop a laser profilometry based endoscopic profiling. After I'll discuss how this method operates, and after that, after getting those images, there is a need to do the defect localizations and there's a need to classify among various defect categories, so that to consider or exploit both the spatial and temporal features that are getting embedded in the images. And after that, I have compared with other deep learning and machine learning models. But however, it has to be noted that developing high quality experimental data in a lab is a very much challenging job to do. So this is basically the setup of a schematic of a plastic pipeline. You can see where we have the laser source as the diode and the CMOS lens to capture the laser rings. Now, if the laser diode projects circular patterns of light on the endoscopic pipe walls, cylindrical pipe walls, and whenever a defect comes on the endoscopic regions of the pipes, that will cause a distortion in the laser rings as follows, and that are captured by the CMOS lens. Now, this network is easily adapted to work across pipes of varying diameters. Only one thing that has to be altered to work across pipes of various diameters is the distance between the laser diode and the CMOS lens. So, and from the algorithm side, it can provide an online mode of assessment that can provide efficient defect localizations and the classifications on the out of sample data sets. And our algorithms are robust to the various fluctuations in the gantry speed and also the laser intensity. So here you can see the experimental setup, and this is the gantry, which consists of a metal rod and the laser diode and the CMOS camera. So it is going inside the pipelines to and fro, and that is gathering the data. For gathering the training data, we have used pipes of diameters of 10 to 15 centimeter diameter, whereas for our test purpose, we have used pipes of diameters 18 and 20 centimeters. Now, as you can see, whenever a defect will come in the endoscopic pipe wall, that will cause a distortion in the laser rings. Now, these are the various sort of defects, man-made defects that can happen within the plastic pipelines. One is the bump, dent, holes, and slits. And these are the various distortions because of the bump, the holes, you can see the dents, and also because of the slits. And this is the non-defect defect category. Now, there is a bottleneck in my sensor. The bottleneck is that the metal rod is not transparent. It is a non-transparent metal rod. And because of that, in every images, the metal rod is causing a permanent distortion, as you can see from here in the laser rings. Now our algorithm is intelligent enough to capture this distortion and treat it as a non-defect category. However, if a defect gets superimposed with that portion of the metal rod, then it won't get recognized. For that, in our future cases and in our future project, we are developing a transparent. This can either be solved by developing a transparent metal rod, or by placing the laser rod, the laser diode, and the camera in the same direction. After gathering the data, I have developed a gamut of algorithms just to see how our algorithms is featuring in doing the defect localizations and thereby by doing the classifications. For this, I have started with the naive 2D CNN models first. Due to the dearth of time, I'm not going into the details of each of these simple models. And I'll discuss a bit about the optimized model here. So first of all, we have started with a 2D CNN model, and then due to the to make it faster, in order not to learn the weights from the scratch, I have used some sort of pretend weights based upon the image data sets, based upon the V16 based transfer learning model, where we are retraining the dense layers, but we are learning the weights from these pretend weights. But here from these algorithms, we found out that we are not localizing on the circular laser rings, and there is a need to do the defect localization so that to differentiate among the subtle defect categories. For that, I have developed another architecture of a structure-active CNN plus LSTM framework as follows, where first of all, by a circular half transform based PHR extraction method, we are finding out the circles in the image so that it draws the circles at certain radius by traversing the edge of an input image by some sort of accumulator or voting procedure. Then the points at which all the circles intersect gives us the center by that voting procedure and also the radius. From that, we are finding out. After that, to focus much more on these laser rings, what we are doing, we are segmenting that into these laser rings into 20 rectangles, so that to focus much more on the region of our interest, and after that, so that we can focus much more on the region of interest. After that, what we are doing, we are passing each of those frames into a time distributed sequential architecture of 5 convolutional layers, and after doing a flattening, we are then feeding them to a sequential LSTM architecture to find out the temporal correlation among each of the frames. But by doing that also, we find out that we are not getting optimized coverage, and also the exceedance were pretty high that I will discuss. For that, in order to do a better defect localization, there was a need to develop a cross-layer hierarchical bilinear pooling, where we are doing a fusions of various interlayer PHR interactions by focusing much more on the crucial local part of the object. How we are doing that? We are doing that in 3 blocks. In the first block, we are extracting the PHRs by different convolutional layers, or we are extracting those PHR maps. Then we are projecting them to higher dimensions by independent linear mapping, where the PHR attributes from different layers are expanded to higher dimensions to capture the detailed components in the image. Here you can see by a visual map by one such defect category in the projection layer that our algorithm is able to focus much more on the local PHRs and the distortions in the laser rings. After that, in the projection layers, what we are doing the every 2 projected PHRs are pixel-wise multiplied in the 3rd stage to get the interacted PHRs. And after that, we are applying the same average pooling based on the softness-based classifications to do the classifications among various defect categories. So these are basically the mathematical equations that is governing the conditions that are happening in these three blocks or in these three stages, where in the first stages we are getting the THR maps. Then what is doing after that, where WI is the unknown projection matrix. Now, this position matrix can be written by a keyword decompositions, can be factorized into two unknown vectors as U and V matrix as follows, which are projected to higher level, higher dimensions, while Euclid and Euclid allow much higher dimensions than that of U and V. After that, what we are doing in the projection layers, from the same spatial locations, the different projection layers are element-wise multiplied to find out the element-wise process that we are getting from here. After that, in the final stages, we are doing the estimations of the Y. So this is basically the architecture wherein we are following a decimal 50 architecture, which comprises of 48 convolution layers. And after that, they are projected to a higher level projections based upon this, where P is the tuning parameter in our model. And after that, we are doing the interactions among different element-wise multiplications. And after that, they are passing on to the average pooling for the shrinkage, and finally for the softmax-based activation. Here we are just showing showing our results in terms of the test data set across both the accuracy and the loss by the different optimized deep learning models, where you can see that our cross-layer based HBB model is giving us better accuracy, around 15% more accuracy than that of the naive 2D CNN. And though it is not actually fair to compare our algorithms with that of the other naive machine learning algorithms, but though we have compared it with the other machine learning algorithms, and we are getting around 25% better accuracy than that of the best optimized support vectorization model. However, as I have told, that the accuracy and the loss are not the true performance metrics to judge how fair our algorithm is behaving for our NDE datasets, because in NDE we have to give the results in the terms of the coverage and also the exceedance, also the false positives. So for that case, actually, later I have done a binary classifications on each defect categories, as you can see, based upon the precision and the recalls and also the ROC calls. They are actually in the bottom. I am showing by our optimized HBP model, whereas this the top one is by a 2D CNN and this one is by the CNN plus transfer learning model. While you can see in our optimized model, the dip in the dip is happening above 90% case, more than above 90% the dip is happening. So from here we can conclude that our optimized model is having higher coverage and low exceedance. So in my final project, actually, I'll just go, due to shortage of time, I'll just discuss a brief about what we are doing over here. So we are developing a fusion method based upon a multimodal defect detection scheme. Here, because sometimes to do the defect localization and detection under several conditions, because different sensing techniques are heterogeneous, because the outputs are heterogeneous, so different techniques are sensitive to different parameters. Hence, there is a need for better defect localization. There is a need to do certain sort of fusion. So what are the advantages of the fusion? Say this is the source 1 and this is the source 2 of the multimodal inspection techniques. When this goes to the data fusion center, from that we can get two sorts of information. One can be a complementary information, another can be a redundant information. The complementary information means the information that is unique to each of the sensing technology. And this complementary information increases the accuracy of your inspection. Whereas the redundant information means, here you can see the information that is common to both the sensing techniques. And that will increase the reliability of your inspection. Now, why is fusion needed? The fusion is needed because sometimes the inspection techniques, these heterogeneous inspection techniques, contain certain defect characteristics that are complementary to each other. Fusion will be efficient under the noisy regime as it will increase the SNR, and also it can help in better identifications of the defect dimensions of the submillimeter surface and subsurface defect. So here from this some simulations in the console, you can see what the inspiration of doing a fusion, as this is an eddy current inspection technique, as this is a result for a magnetic flux leakage for a defect of width 0.2 millimeter and depth 0.5 millimeter. As you can see, the spatial resolution of the magnetic flux leakage technique is poor. However, after doing a fusion by pixel level data fusion by using a state-of-the-art sparse representation technique that I will discuss later, we can get better defect localization and also with an improvement of the SNR. So this is the heuristic of the schematic that we have undertaken over here in the fusion work. First of all, I have developed the NDE techniques and I have done both the simulations based upon each inspection techniques, and also I have developed the sensors in our lab. After that, I have done the scanning of various steel samples and also the pipeline based samples. And after that, here we have done a pixel level image fusion. But before that, I have developed a nice database filling rule that will tell us in which case we need fusion and when fusion is not needed, because there can be some boundary cases when there is no when one of the methods can fail. In that case, there is no need of developing doing the fusion, and our database filling rule will tell us to give weight as 1 to the successful inspection technique and weight as 0 to the failed technique. After that, in the experimental, this sort of actually there can be another condition that can arise on in terms of misregistration. This can happen in terms of the experimental images, because the sensor are always not always in the center of the scanning area. Hence, there can happen that there can lie some sort of offset. So there is always a need to develop a registration model. Here I have done the registration based upon anchoring, where I have anchored the MFL image as a reference image, and based upon that I have done the registration of the eddy current based upon a DFT technique. And also I have done another sort of registration based upon an optimal transport technique, where we are transferring the masses of each of the distributions between two of the experimental inspection techniques. And this optimal transport will be beneficial under the boundary conditions when one of the method fails, and our fusion screening rule tells us to give weightage as 0 to the failed method. After that, we are doing incorporations of the NDE knowledge, and then we are applying the state-of-the-art pixel-based fusion algorithms, which are basically some spatial domain-based, where we are applying kernel-based filters as discussed above in my ensemble of filter approach. And also we can apply some sort of transform domain, where we are transforming our data in some sort of sparse domain or some sort of wavelet-based domains also. And then we are doing the fusions of the detailed coefficients and also the baseline coefficients. And after that, we are giving the results in terms of the performance metrics. Now, what is the trade-off? The trade-off between these sensing techniques are as follows. Because method MFL fails to detect the defects which are lesser than some shallow defects, lesser than 0.05 millimeter depth. And in our sensor, the eddy current has poor spatial resolutions, as it fails to detect the lesser width defects which are lesser than 0.05 millimeter width. And it is also to be noted that the output of the MFL method are the magnetic flux leakages, whereas for the heterogeneous eddy current is either it can be complex voltage or the complex impedance. So here I have developed, first of all, I have developed a naive database cleaning rule, which is constructed by looking at the difference in the standard deviations of the signal readings when there is defect to that of the defectless background scenarios. Our database cleaning rule is telling us to choose eddy current only under this scenario, or to choose MFL under this scenario, whereas it is telling us to choose both the eddy current and the MFL under this scenario. Now here in this schematic, you can see this is the console 3D console multiphysics simulation model of the MFL that I have developed in console. Now, and this is the sensor that I have developed for the experiment. That this has been developed in SolidWorks. This is the holder to hold the two NDE magnets, permanent magnets of opposite polarities facing each other. Now, when we are scanning a conducting specimen, the magnetic fluxes will flow from one pole to the another polarity. When there is a defect or some disturbance in the sample counts, then the magnetic flux leakages will be disturbed, or there will be some perturbation in the magnetic flux leakages that are captured by this Hall, that can be captured by a GM or giant magnetoresistance sensor or by a 3D Hall effect sensor. So that means we can capture the magnetic field both in the axial component, the radial component, and also in the tangential component. And this is the schematic of the schematic.
Can I ask a question?
Yeah.
Because here you have the defect is a surface defect. The defects could be also inside.
Yes.
Subsurface. Okay. Thanks.
Yes, that's a very good question, Professor. For the subsurface defects, we can do actually the multiple modalities based upon the various frequencies also, right? So based upon the frequencies means the skin depth will come into play over there. So we can choose multiple frequencies, and based on that, we can do a multimodal fusion, because it also depends upon the penetration depth also. Yes. So you can see from here that eddy current works on the principle of the Faraday's law and also the Lenz's law, where we are using an ER-quiet code with numerous terms. So first of all, we have to give feed an AC current, and that will produce the alternating magnetic field. So when a conducting specimen comes due to the presence of defects, the alternating magnetic field will result in the generation of AC current, and the direction of the AC current will be in a direction opposite to that of the source current. And that is the phenomena or the working principle of the eddy current. So for our experimental, this is a single coil that has been generated for the simulation purpose, you can see. Whereas for the experimental purposes, we are using an edify system that consists of an array of EC probes, where in each row we have 16 number of coils, and that comprises of 2 rows. Here you can see for the experiment how we are doing the experiment. So we are scanning a sample. Here. So it can be done on the, as Professor has mentioned, that can be done on the near side scan also, and also we can just invert the sample, and also we can do the from the opposite side, and that can be a subsurface defect. So so after that, what I was doing, due to the dearth of time, I'm not going into the details of each of the fusion algorithms, because these are just the state-of-the-art pixel-based fusion algorithms that are basically, that can be spatial domain-based also, or some transform domain-based also. For the spatial filtering, we are just applying some kernel smoothing approach, where we are doing the spatial close, we are taking into account the spatial closeness of the pixels. And after that, we are doing a smoothing of the eddy current image by a MFL image, source image, and vice versa. And after that, we are getting the base layer and the detail layer coefficients and doing the fusion. In the transform domain method, we can transform our image by after doing a Tikhonov regularization into the sparse coefficients, and also we can transform them into the wavelet domain, and also then we can do the fusion. in that way. So these are the, due to the dearth of time, I'm just showing the results of some of the results. You can see that for our experiment, for our simulation purpose, there was no need of doing the registration. And this one is by the source EDICA, and this one is by the source MFL. And after doing the fusion by a CSR-based method, we are getting better defect localization. Also, the HNR is very high. However, for our experimental cases, there is a need to do the registration. As you can see, these are by the source MFL and source EDICA image. And after doing the registration of the EDICA based upon the anchored MFL, so we are doing the, after doing the registration, we are getting better defect localization. Whereas without doing the registration, we are getting bad performance or worse performance. Also, though there is no need of doing the optimal transport-based registration, because here both the methods are able to do the defect detections, but also once we do the optimal transport-based registration, they also, you can see that we are getting better detection result than that without registration. So these are just some sort of preliminary results that I'm showing. And this is just the last work that I'm showing today, where there is a need to do a dynamic defect tracking by NDE-based transfer learning. And here the initial paper of ours has been published in a PHM conference, and I'm working on the journal with the experimental data. So what's the goal? The goal here is that the baseline data, that means the initial data, we are doing the initial scan at a low speed or at less uncertainty. That can be at less liftoff also, or with more step size, or at lesser speed. Then in the later inspection, what can happen? Either the defect can increase in size, or a new defect can also crop in, or the defect can remain constant in size. Then in the later inspections, what we are doing the noisy scan. The noisy scans means the scans at higher speed that will cause noise corruption and also distortion in the magnetic flux linkage signals. Now you can see, first of all, so I have gathered the data by the same MFL approach, where I have developed a mixture of regression model. So this mixture of regression model I have fitted on this baseline scan, that means on the noiseless data, to find out the defective and the non-defective areas. The mixture regression model, based here there are two clusters. Either a point can fall in a defect cluster or in a non-defect cluster. Based upon the mixture regression model, we are getting the posterior probabilities, and then we are telling either point to be a defect or a non-defect based upon that. So our mixture regression model, as you can see from here, works better when there is no noise. That means on the baseline information. But when at the later inspections, when the data becomes very much incorporated with noise, then our mixture regression fails completely. Then there is a need to do a transfer learning. How we are doing the transfer learning? Here we are transferring the location and the size of the defect that we are learning from our day 1 to our later inspections, that I'm telling as day 2 or the day 3 in the corresponding days or the corresponding inspection. Say from this dummy schematic, it is the defect area, and this is the non-defect area that we have recognized by a mixture regression approach. After that, what we are doing, we are projecting these defective areas and the non-defective areas on the later inspections, where by these dots, I'm demarcating it by that of the noisy areas or the noisy scans. Now, here I am telling that the defect can, this is the tuning parameter, where I am telling that the defect can actually increase in this neighboring area. This is the tuning parameter in our model. After that, what we are doing, we are just applying a linear regression. We are doing a linear regression where we are regressing out the values of MFL values from the later inspections by the previous baseline inspections, and we are changing these values by the predicted values that we are learning from this regression model. By doing that, what will happen? in this area, and in the non-defective area, the data will become denoised. And as the amount of the denoised area has been significantly increased, only the noise can remains within this neighboring area, then we can easily apply the mixture regression approach again, and we can classify these points to be to fall within a defect or a non-defect cluster. But later actually I figured out, right, that again here the difference from our first project with that project is here we have the prior information, that means the information from the baseline scan to be noted. But here also what I am doing on the neighboring areas, I am doing a point-wise classification. Okay, but when the neighboring area becomes very much noisy actually, then also the posterior probabilities are telling a point to be defect or non-defect based upon these are t-test, because here the noisy areas become very much noisy, right? Then that can be a erroneous problem that can happen. So where the alternate hypothesis is coming from the defective areas, and the null hypothesis I'm telling from the non-defective areas. So what I'm doing right now, instead of doing a pointwise classification, I'm trying to tune a model based upon, instead of taking a pointwise classification, can we take a kernel of weights or an area, right? Based upon that, whether we can tell about the unclassified areas, so that where that will happen, that the mean of the distributions will remain the same, but the variance will decrease by the number of points we are taking in this model. So that I'm currently doing as of now. So yeah, this is some of my work that I have done, and I'm open to take the question. Thank you.
Thank you, Subrata. Do we have questions? George is there.
Well, I think maybe I don't know if Raj is on the call. Maybe he would have some comments.
Yeah, I just had one question, Subrata. This is Raj from Brown. On slide 25, you mentioned the LSTM architecture. So maybe I missed something. So what is the transient term in your data?
Just model. Yes, that the transient terms are basically from the each of these frames, right? We are feeding into the bunch of convolution layers, and after the convolution layers, what we are getting the output of each of these frames, right? So now there lies a spatial relationships among these frames. So in order to learn that relationships, I was just applying an LSTM layer based upon the PyTorch model, because I didn't actually implemented this model back from the scratch. But there also I find out that this model is very much actually it is a burdensome model to learn, and it is not able to localize the certain defect categories that I was planning to have. That's why in order to understand the several interlayer PHI interactions that is happening across various PHI maps, so there was a need to develop a spatiotemporal model. That's why I developed the later model. This is just a model for the comparison.
So what is this field evolving? Like, is this a physical field which is evolving with time?
Yes, no. The physical means not the here the temporal relation among the frames. So what is the location among the defined frames? So
Okay.
that we can track there is a by the discontinuity, the crack or some sort of thing that we are trying to.
I think what you're doing, you're moving around the edge, right? And you take segments of it. Yeah.
Okay.
So that's the time component, the pseudo time.
Yeah.
Okay. So just a comment, like what happens like if you have multiple defects of different scales in the sample?
Yes. So multiple defects also, we have taken multiple defects of various scales. So the problem is that our algorithm is working better when there are some endoscopic defects. Endoscopic means on the inner pipe wall, but when the defects are on the outer pipe wall, and if it is not through wall defect, then this simple laser profilometry based setup will not detect the defects. So that's a problem with this setup, but it is working well for doing the defect detections of various dimensions on the inner pipe wall. But I think another better approach, because I didn't think of that in that way during that time, or I didn't do much of the literature survey. Also, we can do some sort of defect tracking also, so that we can track how much the defect is growing. Also, we can do that also by some sort of algorithm. But as I have told that here I'm getting the stagnant pool of data, because in our experiments, it is very hard to get a a continuous pool of the experimental data. But if we can get a continuous pool of the experimental data, then we can also track how the defect, say a defect is, how much a defect is increasing from the n-1 time to the nth time. That we can, I think that can be a interesting problem to figure out in the later stages, if we have an abundant pool of actually online data that is coming to us.
Okay. And there is also just a comment to that. There are some papers, a paper published in Advanced Sciences on computing the stress localization for multiple defects. Maybe that could be one of the methods you can try. So, sure. Thanks.
Subrata, so you have multiple modalities, magnetic fields and so on, and but I was wondering if you consider what Raj who just asked the question. In his paper he introduced physics, right? So then he could reduce the amount of data by a big factor, but also you can sort of if you don't know the answer, right? If you don't know the defect, you could sort of use the physics to safeguard your answer.
Yes.
Have you considered that? Because you have a lot, you're sitting on a lot of data.
So actually in our lab, as we have our NDE lab, right? So that's a very good question, Professor. So our goal is to, first of all, we have to develop the sensors, because our industrial partners are actually want to see how that, by doing the imaging, how much defect we can track, whether we can image those corrosions, or we can see where the tip of the crack lies, whether we can track those or not, right? So first of all, our goal is to develop these sensors in a way. And as you have mentioned, so one of our project, actually we are trying to figure out how the interactions are happening about among certain threads. So say a corrosion is happening at a crack tip. Okay, Professor. So there, can we do some sort of physics informed neural network or something, so that how the crack propagation is fastening up because of the crack. So, and what the interaction is happening among them, we are planning to study. And also we are planning to study in the hydrogen defects, how the hydrogen embrittlement and hydrogen induced cracking, this sort of actually when there is a hydrogen transport is happening, where there is some sort of crack or pollution, then how this is actually worsening, and how fast the defects are increasing in size. That we are trying to figure out by some sort of physics informed neural networks. So that is our future.
The dynamic problems is also that's where physics would help a lot. You're right. Yeah, some data is listening. She's working on modeling cracks with pins, but also I think Raj could also help.
Yes, thank you, Professor. Thank you.
We'd be happy to collaborate. Actually, you're sitting on lots of data. You develop all these techniques yourself. So this is very impressive, actually, what you have done. This is like two theses, in my opinion. These are two PhD theses in one, not one.
Thank you. These are some sort of works that we are doing over at NDE.
We have more questions for Subrata?
I had a small question. This is Varun from Brown. Hey, Subrata. So I think one of the things that people often encounter when they're doing failure detection is how do you differentiate between like an actual fault versus a sensor error? Have you taken that into account do you calibrate your sensor every time you do a measurement, or how do you take that into account if your sensor is not faulty?
Yes. So in one of our talks, actually, when we are taking into incorporation various sort of uncertainties, then we didn't do the calibration because there are some drift in the probes also in my first project. But in the later projects, actually, I have done firstly the sensor characterization and also the calibrations. For say for the eddy current, we have done in-phase calibrations and also the peak voltage. And after that, we are using that array of sensors. That's a very good question.
Okay, well, thank you.
So if we have no more questions, thank you, Subrata, for tuning in today and giving us this wonderful presentation.
Yes, thank you, Dr. Gushan. Thank you.
With that, we come to an end for today's seminar. I would be uploading the recording of today's presentation on our YouTube channel. And every one of you have a great weekend and have a great rest of the day ahead.
Yeah,
Bye.
thank you. Thank you.